Imagine a multi-user online game. The game space is a database shared by all players. To allow everyone to see the same state of the game, one could centralize all the data in a single server. Unfortunately, beyond a few hundred users, the load is too high and the furthest players suffer from network delay. A solution is to distribute the database over several geographical locations close to its users. Designing a system that is both available and correct is a major challenge. There are currently two main types of distributed databases: strongly consistent and eventually consistent. A strongly consistent database synchronizes updates across replicas. As it behaves like a centralized system, application programmers make few mistakes. This kind of database requires frequent synchronization. In the event of a network failure, a strongly consistent system can become completely unavailable. A strongly consistent database is safe, but slow and inefficient. On the other hand, many cloud database systems are eventually consistent. An eventually consistent database accepts updates in parallel without any synchronization and is therefore efficient, responsive, and always available. However, this kind of system delivers updates in any arbitrary order, and when replicas diverge, it reconciles concurrent updates in some arbitrary way. It is up to the application programmer to compensate for these defects. This is error-prone and can lead to corrupted data. An eventually consistent database is fast and efficient, but it is complex to manage for programmers and for users. Here is an example. Eventually consistent database BuggyDB comes with a default admin password and admin login disabled. Alice, working from the Alicante replica, sets the password, then enables login. BuggyDB does not make these updates visible in the same order. Malicious user Bob, who is accessing a replica in Berlin, notices that admin login is enabled, but the password change has not been propagated yet. He successfully gains full control with the default password. Antidote constitutes a sweet spot between these two approaches. Antidote accepts parallel updates and is geo-distributed near users. Therefore, Antidote is available under partition, efficient and responsive. At the same time, Antidote avoids anomalies thanks to the following features. It merges concurrent operations according to their semantics. It groups related operations into atomic transactions. And it delivers updates in causal order. A database site is strongly consistent, and selected operations can be strongly consistent system-wide. In the same example as previously, but this time using Antidote database, the security violation does not occur. Because of its guarantee of transactional causal consistency, all users who observe login enabled also observe that the password has changed. Antidote is a component of a new approach called just right consistency. The idea is to fine-tune the database to the consistency needs of your specific application. Static analysis determines which critical operations must be strongly consistent. For instance, consider a merchant website that sells concert tickets. The more tickets are sold, the fewer seats are available, and the more the database has to be synchronous. When the merchant gets to selling the last available ticket, the database needs to synchronize tightly to avoid selling it twice. Antidote is open-source software, available under a permissive license. The core of the database system is written in Erlang, but applications can use any language, for instance, Java or JavaScript. The Antidote team is committed to code quality and good engineering practices such as layered structure, code reviews, test suites, etc. Antidote is a geo-distributed cloud database that is highly responsive and available under partition, yet offers strong guarantees to applications. Antidote is ready for use today for your large-scale applications. The Antidote community is in full development, so join us!